Hello everyone. In this video lecture we look at one of the important concepts in this units and measurement chapter, which is dimensional analysis. Now there are a lot of applications of dimensional analysis across the chapters. That's why this is a very important tool in physics. So what is this dimensional analysis? Dimensional analysis is based on the idea of dimensions. Now when we have a derived quantity, this can be expressed in terms of the fundamental quantities, basically the relation between the derived quantity and the fundamental quantities to which it is related, and it is written as a product of powers of the fundamental quantities. Now when we express this as a product of powers of the fundamental quantities, the powers to which each of these fundamental quantities are raised in order to write this particular expression, these powers are called as the dimensions. To understand this in a little bit more detail, let us look at an example. Okay, so if you talk about force is mass into acceleration. Acceleration is nothing but rate of change of velocity, so I can write it as velocity by time, and velocity is displacement by time. So in terms of the physical quantities, it is nothing but length by time. So overall what we will be having is force is equal to mass into length into time power minus 2. So the powers of the fundamental physical quantities are the power of mass is 1, and the power of length is 1, and the power of time is minus 2. So these are basically called as the dimensions. Now the dimensions of force are 1 in terms of mass, 1 in terms of length, and minus 2 in terms of time. So this will tell how a particular derived quantity is dependent upon the fundamental physical quantities. This is in short what is the dimensions of a derived quantity. Now this can be also expressed as a formula by using something called as dimensional symbols. All the fundamental quantities, length, mass, time, current, temperature, amount of substance, and even the luminous intensity. Of course, the reason why we are not focusing on luminous intensity over here is in our entire higher secondary syllabus, there is not much importance for this quantity. But all the fundamental quantities are given dimension symbols. The symbol for the length is L, mass is M, time is capital T, electric current we can use either A or I, temperature we will use K or theta, and quantity of matter or the amount of substance, dimensional symbol is MOL. The two supplementary physical quantities, plane angle and then solid angle, they do not have dimensions, and that is how these two supplementary quantities are different from the fundamental physical quantities. So we can say they are actually dimensionless. Now if we express the relation by using these dimensional symbols and write it as an equation where we can have the physical quantity as well as the dimensional formula within parenthesis, is what we call as dimensional formula, and that equation will be called as the dimension equation. So just to go back and look at what will be the dimensional formula for the force, so we are keeping it within the parenthesis. The relation is mass to the power 1, so we'll use instead of mass we'll use symbol M, and length power 1, instead of length we'll use symbol L, and time power minus 2, so instead of time we'll use capital T. So this is what we call as dimensional formula. So dimensional formula will quickly give us an understanding of how a particular derived quantity is dependent upon the fundamental physical quantities. Now we'll talk about the applications in a little while, but let us go and see what will be the dimensional formulas of some common physical quantities. Let's say for example we talk about velocity or speed. Speed is nothing but distance by time, so there will be no mass involved over here, so it will be m power 0, no mass relation, L power 1, T power minus 1. Acceleration is the rate of change of velocity, so it will be velocity by the time taken. Already velocity is Lt power minus 1 divided by T, so it will be Lt power minus 2, and m power will be 0. Then we have momentum. Momentum is mass into velocity. So mass into velocity, mass will be m and velocity is Lt power minus 1. Then we have impulse. Impulse is force into time for which the force is acting, impulse created by the force. So force already we have ml t power minus 2 into time t, so it will be ml t power minus 1. We can see interesting thing, both momentum and impulse, they have the same dimensional formula. Force already we had a look at it, ml t power minus 2. Then pressure is nothing but force acting on a given area, so it will be ml t power minus 2 force divided by area is L square, so it will be ml power minus 1 t power minus 2. That will be the dimensional formula for the pressure. Kinetic energy and energy in general as well as work, they both have same dimensions, so it will be work is equal to force into the displacement. When we go into the work energy theorem or the work power energy topic, we'll try to understand a little bit more detail about the relation between work and force. Actually work is defined as the dot product between force and displacement, but just here for the quick analysis we look at it as force into displacement, so it will be ml t power minus 2, which is force into displacement is L, so it will be ml square t power minus 2. Then we have power is the work done by the time taken or energy that is used by the time taken, so it will be ml square t power minus 2 divided by t, so it will be ml square t power minus 3. And density is mass by volume, so mass m divided by, so it will be ml power minus 3, and t there is no relation, so it will be t power 0. So broadly when we look at any physical quantity, if we want to get the dimensional formula, we must know an equation where this particular physical quantity is appearing, and in that equation all the other dimensions must be known to us. So that is the approach which we can take to find the dimensional formula for any derived quantity. Now moving on, we can look at some more quantities, especially about the circular motion or the angular motion. We have angular displacement, which is the angle covered, and angle does not have dimensions. It's a dimensionless quantity, so it will be m power 0, L power 0, t power 0. Angular velocity is the angular displacement by the time taken, so it will be simply t power minus 1. Angular acceleration is the angular velocity change divided by the time taken, so it will be t power minus 1 divided by again t, it will be t power minus 2. That is the angular acceleration. Moment of inertia is a quantity that we will be learning in the rotational motion. If you have an object mass m which is rotating at a distance r from the axis, then moment of inertia I will be given as m into the r square. It's a very simple definition. We'll go into the details of it in the particular chapter. So looking at this definition, it will be m L square. That will be the moment of inertia dimensional formula. Then we have torque. Torque is nothing but the force multiplied by the distance, where the distance is nothing but distance between the point where you apply the force to the axis. So it will be m L t power minus 2, already force is there, into L, which will be ml square t power minus 2. Now we can see one more interesting concept here. Torque and energy both will have same dimensions, but they are different physical quantities. Angular momentum, a particle mass m going in a circle of radius r with a velocity v will have angular momentum m into v into r, so it will be m L t power minus 1 into L, so it will be m L square t power minus 1. Then spring constant, if you have a spring, then the spring force will be given by F is equal to K into X, where X is the elongation or compression, which means K is equal to F by X. So ml t power minus 2 by L, it will be m t power minus 2, that is the spring constant. Then we have gravitational constant. We look at what is the approach that we will take to find the dimensional formula for this. Dimensional formula will be m power minus 1 L cube t power minus 2. Then we have intensity of the gravitational field, which is L t power minus 2. Then we have gravitational potential L square t power minus 2. So whichever topic or whichever new physical quantity we are getting, if we have an equation where this quantity is there and all the other quantities are known to us, we will be able to find the dimensional formula. Just to give you an idea of how do we find the dimensional formula for the gravitational constant. So Newton's law of gravitation says that the force between two masses m1 and m2 which are separated by a distance r will be given by F is equal to G m1 m2 by r square. Now in this formula, other than G, all the other quantities dimensions are known to us. Force dimension is known to us, m l t power minus 2. Mass each will have dimension m and distance dimension is L. So by this we will be able to find what will be the dimensional formula for the G. So dimensional formula for G will be force dimension into r square by m1 into m2. So force is mlt power minus 2 into r square will be L square divided by both our masses, so m into m square. So finally we will get m power minus 1 L cube and t power minus 2. That will be the dimensions of the gravitational constant G. So this way, any physical quantity given to us, we will be able to find the dimensional formula by using this relation. Now even when we go to the other topics, especially the properties of solids and properties of fluids, we are going to be encountering quantities like surface tension, which is nothing but force that is acting per unit length. So it will be m L t power minus 2 divided by L, so it will be m t power minus 2. That will be the dimension of surface tension. Then in the fluid motion we have a concept called as velocity gradient. It's nothing but change in velocity per unit distance covered between the layers of the liquid. So it will be L t power minus 1 divided by L, which is simply t power minus 1. That will be the dimension of velocity gradient. We have coefficient of viscosity. It's nothing but the measure of how viscous a liquid is. We have an equation called as Stokes law, where the viscous force acting on a spherical body moving in a liquid with the radius v with the radius r and velocity v will be drag force, or the viscous force will be 6 pi eta rv. So from this formula we will be able to find what is the dimensional formula for the coefficient of viscosity. So this symbol over here will be called as eta, and this represents coefficient of viscosity. So same way as we did in the case of the gravitational constant, in this force is known to us, r is the radius of the sphere and v is the velocity, and numbers do not have dimensions, so we will be able to find the dimensional formula for the viscosity. Then we have stress. Stress is force acting on given area, so we'll have the dimensions of ml t power minus 2 divided by area is L square, so the final dimension will be ml power minus 1 t power minus 2. Then we have strain. Strain is nothing but if we are trying to elongate an object, then change in length by original length will be the strain, which is called as a longitudinal strain. So it will be length by length, which is having no dimensions. So strain is another dimensionless quantity. Then we have modulus of velocity, which is nothing but the relation between stress and strain. So the relation is stress is equal to modulus of elasticity into strain. So from this formula we can get the dimensional formula for the modulus of elasticity. So we can see, since strain is dimensionless, both stress and modulus of elasticity, they will have the same dimensions. Then we have another quantity called as Poisson ratio, which we will be learning about it in this properties of solids. Then we have time period. In oscillations, the time taken to complete one full revolution or path, which is nothing but time. We have frequency, which is 1 by time period. It will have dimensions of inverse of time. So whenever we have a physical quantity, we must have an equation where this quantity is appearing, and in that equation, if all the other quantities have known dimensions, then we will be able to find the dimensions of the unknown quantity. So this is the basic approach to find the dimensional formula for any physical quantity. Now, though we study this topic at probably the beginning of the 11th standard, this is actually a continuous topic. So if we go to any subsequent chapter, we are definitely going to encounter a new physical quantity, and there we must apply the idea of finding the dimensional formula to know what is the dimensional formula for any new quantity that we are going to study. Now, the importance of the dimensional formula is it exactly tells how a physical quantity is dependent upon the fundamental physical quantities. Now there are many applications of this dimensional formula where we'll talk about it in the dimensional analysis part of it. So this is the broad idea that we need to be having to find dimensional formula of any unknown quantity. Now as we saw already, there are some quantities which are having same dimensions, like if you talk about frequency and angular frequency and angular velocity, velocity gradient, and even decay constant, all of them will be having the dimensional formula of t to the power of -1. Work, energy, different types of energies, kinetic energy, potential energy, internal energy, and even torque as well as moment of force, all of them will have same dimensions of ml square t power -2. Pressure, stress, Young's modulus, bulk modulus, modulus of rigidity, all of these are different types of modulus of elasticity, which we will be learning about them in the properties of the solid section. And energy density, so energy density will be energy by volume, all of them will have the same dimensions of ml power -1 t power -2. Then we have momentum as well as impulse, they both have same dimensions of ml t power -1. Then acceleration due to gravity, which is nothing but acceleration, as well as the gravitational field intensity, they both will have the same dimension of L t power -2, which is nothing but the dimensions of the normal acceleration. We have force, thrust, weight, and energy gradient, all of them will have the same dimensions of ml t power -2. Angular momentum, as we saw already, it's nothing but the mvr, mass into velocity of the particle into radius of the circular path. This is the angular momentum formula for a particle going in the circular path. Angular momentum and Planck's constant. So Planck's constant is a quantity that we'll talk about it in modern physics section, where we'll be looking at the properties of the fundamental particles. So Planck's constant is related to the energy as E is equal to h into nu. Energy of a photon will be given by E is equal to h into nu. Nu represents frequency. So from here we will be able to find what is the dimensional formula for the Planck's constant. Both angular momentum and Planck's constant will have the same dimensional formula of ml square t power -2. Surface tension as well as the surface energy per unit area, they both will have the same dimension of m t power -2. And strain, refractive index, all the relative terms, relative density, relative permittivity, relative permeability, and plane angle, solid angle, distance gradient, all these are actually dimensionless quantities. So they don't have any relation to mass or length or time. So these are some of the quantities which are having the same dimensions. Now moving on to the most important segment of this study, which is the dimensional analysis. When we talk about the dimensional analysis, it basically follows the two important principles. They are, if we have an equation, now equation will have two parts, the left hand side and the right hand side, LHS part and the RHS part. So if I say, for example, x is equal to y, I can even say x is equal to 2y, forget about the numerical constants here. So if I am saying there is an LHS and there is an RHS, I can say length is equal to length. I can say time is equal to time, but I can never say length is equal to time. This is not possible. Which means if we have an equation, then the LHS and the RHS part must belong to the same physical quantity, which means they will be having the same dimensions. The second important principle in the dimensional analysis is, when we are adding two quantities, let us say we are adding A and B, or when we are subtracting two quantities, let us say I am subtracting D from C. This can be only done when the quantities are referring to the same physical quantity, which means I can add A to B when A and B are referring to the same physical quantity. I can subtract D from C when C and D are same physical quantity, which means I can add length to length. I can subtract length from length, but I cannot subtract length from time. Which means when I am adding two quantities or when I am subtracting, then the quantities which are added or the quantities which are subtracted, they must be having the same dimensional formula. So these are the two basic principles which we will be using in the entire dimensional analysis aspect. Now, dimensional analysis is a set of useful results which we will be able to have based on the two principles. First, the use of the dimensional analysis will be to find what will be the unit of a physical quantity in a given system. Let us say, for example, we want to find what is the unit of the force in CGS system. CGS system is where we have length unit is centimeter, mass unit is gram, and time unit is second. Dimensional formula for force is mLt power minus 2, which means it will be gram centimeter second power minus 2. So this way we will be able to find what is the unit of a physical quantity in a given system of units, and this is actually called as a dyne. So the CGS unit of the force is called as a dyne. So this is the first application of the dimensional analysis. Now, the dimension analysis can be used to find the dimensions of a physical constant or a coefficient. So how do we go about using this particular idea? Now, this is what we have been talking about when we were trying to find the dimensional formula for the unknown quantities. Now we will go to the quantity that we have already referred to, which is coefficient of viscosity. Coefficient of viscosity is a measure of how viscous a particular liquid is. We have a formula called as Stokes law. Stokes law is, if you have a spherical object of radius r which is moving with a velocity v in a fluid, where the coefficient of viscosity of the fluid is given by the symbol eta, then the Stokes law formula says that the viscous force acting on the sphere will be equal to 6 pi eta rv. So on the LHS we have the dimensions of mL t power minus 2 force is equal to 6 pi is dimensionless, dimensions of eta into dimensions of r is length, and velocity is L t power minus 1. So looking at just the eta, we want the dimensions of eta, so we'll bring the other two to the LHS. mL t power minus 2 divided by L square t power minus 1. So the Feynman dimensional formula for eta will be m L power minus 1 t power minus 1. This is the dimensional formula for the coefficient of viscosity eta. So this is the approach that we will be taking. If we know an equation where this quantity is appearing, then from the principles of the dimensional analysis, both LHS and RHS must have the same dimensions. By rearranging the terms, we will be able to find the dimensions of the unknown physical quantity. So this is the approach to find dimensions of a physical constant or a coefficient. Now dimensional analysis can also be useful to convert a physical quantity value from one system to the other. Now what we mean to say by this is, if we talk about for example 10 centimeters, which is the length of a particular object in the CGS system. Now the same distance can be measured in the SI system and we will have the value as x meters. We would not know what is the value of x, and using the dimensional analysis we will be able to find the value of x. So how do we go about doing it? For this we will use the basic idea that the total measured value must be same across the systems. Means if you have 10 in centimeter units, means 10 times of the centimeter, which is the measured value of the particular quantity, must be equal to x times of the meter length. Means to generalize it, in any system, if say for example the unit value is u1, another system the unit value is u2, the measured value in the first system n1 multiplied by u1 must be equal to the measured value in the second system multiplied by u2, which is the unit value in the second system, because the total measured value must be same across all the systems. I mean, if I am talking about measuring a length, whether I measure the total length value in the CGS system or SI system or in even FPS system, the total length value must be the same thing. So we will see how we can use this particular idea to find or to convert a physical quantity from one system to the other. Let's say we have the conversion of Newton into dyne. Newton is the SI unit of force, which has the dimensional formula for mlt power minus 2, and 1 Newton is nothing but kg meter per second square. If you look at dyne is a CGS unit of force, which is gram centimeter per second square, or no, gram centimeter second power minus 2. This is the CGS unit. Now let us say, for example, we have the value in the SI system which is Newton is N1 into kg meter per second square is equal to N2 into gram centimeter per second square. So N1 value will be equal to N2 into gram centimeter per second square divided by kg meter per second square. Second square will be cancelled. So what we will be having is N2 into gram by kg into centimeter by meter, which is nothing but we'll have N2 into, so gram, 1 kilogram is 10 power 3 grams, and 1 meter is 10 square centimeter. So gram will be cancelled, centimeter will be cancelled. What we have is N2 by 10 power 5. So the value of force N1 in the SI system, which is Newtons, will be equal to the value in dynes divided by 10 power 5, which means if I say that I have a force of 10 power 6 dyne, the value in the SI system will be 10 power 6 divided by 10 power 5, which is 10 Newtons. This is the conversion for Newtons into dyne, and this approach can be taken to convert any physical quantity measurement from one system to the other system. The idea that we will be using over here is the measured value in any system multiplied by the unit value will be equal to measured value in another system multiplied by the unit value in that particular system. So this is the approach that we can take to convert the Newton into dyne or dyne into Newton. Okay. Now the other important dimensional analysis application is to check whether the given relation is correct as per the dimensions. Now here we are very careful. We are not saying that we can check whether the given equation is correct. We are only saying that we can check whether the given equation is correct as per the dimensional analysis. What do we mean to say by this? Let us say, for example, we have been given an equation that displacement is equal to ut plus half at square. So this is the equation that we will be having in the kinematics. So we need to verify if this given equation is correct or not. Now S is the displacement, so it will have the dimensions of length. The second term which is over there is u into t. U is what? Lt power minus 1 velocity into time is t plus half. Number does not have dimensions. Acceleration is Lt power minus 2 into t square. T power 2. So if you see on the LHS, we have the dimensions of length is equal to dimensions of length, because the t power minus 1 and t power 1 will be cancelled, and here t power minus 2 and t power 2 will be cancelled. So again we have length. So what we are basically concluding is the LHS dimension is equal to RHS dimension, and also here we have two terms and we are adding the two terms. The dimensional check here is when I am adding two terms or subtracting two terms, both the terms must have the same dimensions. So here I have the term ut having dimensions of length, time half at square also having dimensions of length. So we are able to conclude that this equation is dimensionally correct. And to verify whether the given equation is dimensionally correct or not, we have to basically check on the following things. Whenever in an equation any terms are added or subtracted, we have to check that they all have the same dimensions. That is the first thing. Second thing is, when we have an equation, the LHS part and the RHS part must have the same dimensions. So when we are able to verify these things in a given equation, we can conclude that the equation is dimensionally correct. Now having said that, we will never be able to verify if the given equation is fully correct. Why? if the equation has numerical constants, like in this case there is a constant half. If somebody gives us an equation s is equal to ut plus at square and asks us to find whether this is dimensionally correct or not, we will still be able to conclude and say that yes, this equation is dimensionally correct. But the equation may not be totally correct, because whenever we have the numerical constants or numbers, the dimensional analysis will not be able to verify the correctness of the numerical constants. Not only that, in equations where there are physical quantities having no dimensions, dimensionless quantity like angles or strain, I mean we have seen examples of that. Even in those cases, the dimensional analysis cannot verify whether the correctness of the equation is valid, including the constants and dimensionless quantities. So this is about how do we find the correctness of a given equation as per the dimension analysis. Now we can find the relation between different physical quantities. Say for example, while we are trying to understand what will be the correlation between different physical quantities, we may have to know how they are all related. And dimensional analysis can help us in finding the relation between them or in trying to correlate the physical quantities. To understand this, we'll just take a look at this particular example. Let's say we have a simple pendulum. A simple pendulum is basically we have a rope to which a bob is suspended. Now when we give a small displacement, we see that the bob will be having the to and fro motions, and that is what we call as a simple pendulum. So simple pendulum time period means that the time it takes for the bob to complete one full revolution. Time period for the simple pendulum, let us say, is dependent upon the following parameters, because we have mass of the bob over here, the length of the rope, effective length, and the other factor here that is making the bob to move is acceleration due to gravity. So here what we are saying is the time period depends upon the mass of the bob, effective length L, and acceleration due to gravity G. So the approach is if the relations are simple relations. When we say simple relation, let us say for example, if the time period is related to the following quantities as a product of the powers. This is what we mean to say by the simple relation. I can write time period as C is a constant, into the mass of the bob power x, length power y, and the acceleration due to gravity power z. So this is what we call as a simple relation, and the dimensional analysis itself, right, is valid only for these kind of simple relations. And that too, we will not be able to find what is the value of the numerical constant C. So let us see how do we go and find out the values of x, y, z. If you are able to find the values of the powers x, y, z, then we will be able to know what is the relation between the time period of the simple pendulum to the mass of the bob, effective length, and acceleration due to gravity. On the LHS we have time period, means the dimensions will be the dimensions of the time. On the RHS, C is a numerical constant, doesn't have dimension. M represents mass, so it will be m power x. L represents length, so it will be L power y. G is acceleration due to gravity, so L t power minus 2 whole power z. Now by arranging the powers of m, L together, you will have m power x, L power y plus z, because there will be L power z coming over here, and t power minus 2z will come. When we compare the powers of m, L, t on both sides, on the LHS side actually the power of m is 0 and the power of L is also 0 and power of t is 1. So if we try to correlate the powers of m, L, t on both sides, we will have straight away x is equal to 0 and y plus z will also be equal to 0. From the power of t we have minus 2z is equal to 1, which means z is equal to minus half. If z is equal to minus half, since y plus z is equal to 0, y will be equal to plus half. So the relation is time period of the simple pendulum will be C numerical constant, mass of the bob power 0, so there will be no relation to the mass of the bob, L power half, and G power minus half. I mean power half means it will be root power minus half means it will be 1 by root of the particular term. So what we'll be having is t is equal to c into root of L by g. So if you look at the actual formula which we will be learning in the waves and oscillation chapter, the actual formula is time period is equal to 2 pi root L by g. So we are not able to find out what is the value of the numerical constant, but we are able to find the relation between time period and the factors on which the time period can depend upon. So this is what will be the method that we'll use to find relation between physical quantities. And important thing here, the relation must be a simple relation. And when we have a complex relation, this method will not be applicable. The dimensional analysis, though it is a very important tool, it has got some basic limitations because of the way the dimensions are actually defined. The first is when we talk about the dimensions itself are not unique. Like say for example, if we are being given a dimensional formula saying ml square t power minus 2, then this may be referring to work and it may be referring to torque. So if we finally arrive at a dimensional formula in any derivation or calculation, from there we will not be able to conclude what is the physical quantity it is referring to, because it may be referring to multiple physical quantities, since the dimensional formula is not a unique quantity. The second limitation is while finding the relation between physical quantities, or even while verifying the correctness of an given equation as per the dimensions, we saw that we were not able to conclude on the numerical constants because they don't have dimensions. So while we are trying to verify the correctness of equation, or even while finding the relation between different physical quantities, we will not be able to conclude on the numerical constants. This is one of the other limitations of the dimensional analysis. The next limitation is when we want to derive the relation between different quantities, we can only derive the relation which are simple. When we say simple, we are referring to the relations where we have the derived quantity or the unknown quantity which is related as a product of simple powers of the known quantities. So these kind of relations only we will be able to derive. Say for example, I have this kind of relation where displacement is a function of initial velocity, time and acceleration. These kind of equations we will not be able to derive by using the dimensional analysis. Now the dimensional analysis will not give us correct kind of results when we have dimensions where the quantities are similar, and also we have quantities which are dimensionless, like when we are trying to verify the relation between quantities, or even when we are trying to find the correctness of a given equation. If we have these situations where we have dimensionless quantity, or we are having quantities having same dimensions, let us say for example there are quantities having same dimensions a and b. Now we say a power x, b power y. Now if a and b both have same dimensions, then we'll essentially be trying to look at both of them together, and we will not be able to look at them separate. This is one of the other limitation of the dimensional analysis. The last limitation is when we talk about deriving the relation between the physical quantities, if we are confining ourselves to the mechanics, we'll mainly have the dimensions of mlt. So the powers there will be able to give us only 3 equations. If we have relation between a quantity like time period of an rotating body, it depends upon the moment of inertia, the mass of the body, acceleration due to gravity, and then length. So this time period is depending upon 4 parameters. Now since it is all confined to just mass, length and time, here when we equate the powers, we will be only able to get 3 equations. So from 3 equations, there is no way that we can solve more than 3 variables. So this is one of the other limitation of the dimensional analysis, where in mechanics, if you want to find relation between one quantity to the others, the maximum number of other quantities can be only 3. We cannot find the relation if we have more than 3 quantities. So this is the other limitation of the dimensional analysis. Now while there are limitations of the dimensional analysis, this is quite a useful tool in terms of doing a lot of studies with regard to the physical quantities.